Welcome back, everybody. I think, interestingly, for a software development conference, I'm not sure whether anybody has used the word algorithm up to this point. Mark is going to compensate for that now.
Oh, yeah. There'll be a lot of the word algorithm in this talk. So, hello, my name is Mark DeMarco. I'm a UI engineer at Bizarre Voice. We're a company, we do ratings and reviews on product pages for like Walmart and Best Buy and Target and all these big e-commerce sites. And at Bizarre Voice, I've been there for about 5 years. And one of the really interesting things I noticed that one of the transitions that we had at Bizarre Voice is we used to require computer science degrees to even get an interview at Bizarre Voice, and we've backed off that. We feel like we've grown in that sense. We couldn't hire front-end engineers if we were requiring this computer science degree. A lot of front-end engineers, they don't have computer science backgrounds. They come from journalism backgrounds. They come from just high school degrees. They come from anywhere, and some of them are computers. I am in particular computer science, so I was able to get in early enough to watch this sort of transition. I'd say about half of my friends in Austin, Texas that do front-end development, half have computer science degrees and half don't. So when I introduced my talk title, UI algorithms, I had a lot of questions from these two camps. One camp, they knew the algorithm part really well. They were the computer science degree people. They had taken algorithms courses and had beaten in their heads for 4 years, some of them 6. And the other camp, they knew the UI part really well, but weren't really sure what I meant by algorithm. So what I hope to do today is to sort of blend these two camps. I want to show how we can do these really beautiful things in user interface land with computer algorithms. I'll be talking about 2 algorithms today. One of them deals with optimizing hit state, and the other one deals with hierarchical menus. So an alternate title for this talk was A Complete Disregard for Rectangles. That is essentially what we're going to be doing today. HTML gives us rectangles to build websites with. It's just the building block of websites, and that's not conducive to web development, optimal web development at least. So here is a standard website, and here's what I mean by the rectangles that map them up. This is adding a border to everything. Every website is just rectangles. That's how I explain to my non-technical friends what I do, is I build big Lego sets basically out of web pages. This title actually ended up bringing up more questions than it answered, so I'm sticking with UI algorithms. To define an algorithm, this is your standard Wikipedia-style definition of process set of rules to be followed in calculations or other problem-solving operations. It takes input and it produces output. These two probably look pretty familiar to most people in this room. The one on the right is probably most of our textbooks. Anyone's college textbooks for algorithms? So more than half. The one on the left, I've never met anyone who actually has read all of that. I know people who have it, but they use it to raise the monitor on their computers to help with their neck. That's it. However, if I do ever meet anyone who's read those, it'll probably be here at this particular conference. So come find me if you have read those books, and God bless you. So let's take an example of an algorithm. This will be our this is the pseudocode and the style that I'll use. This algorithm, it's pretty obvious what it does. It finds the largest item in a list. It takes off the largest item. It loops through everything else in the list, and if there's anything bigger than the current largest, it just saves it off and overwrites largest. There's nothing special about this algorithm. This is just sort of the style that you'll see. This is not a UI algorithm. The first UI algorithm starts off with these two guys right here. That is Mitt Romney and, of course, Barack Obama. And in 2012, according to the New York Times, between the two of them, they had 512 different paths to the White House. 512 is a suspicious-looking number to everyone in this room. It's a very, very round number. We know it's not really 512 paths to the White House. It's really 2 to the 9 paths to the White House. There's 2 likely ways a state would vote, Democrat or Republican, and there were 9 states in contention, 9 swing states. The New York Times decided to represent this data with a binary tree data visualization. Does anyone remember this back in 2012? Good, good. So a handful of you, which is good. I think right off the bat, this is one of the best data visualizations that have ever been built for the browser. There are a bunch, and they keep coming out with more, and this was back in 2012. I still think it takes the cake for just the best thing, and I'll explain why in a lot of detail. But first, it does an excellent job representing the data at hand, the past at hand. You can see in the top left, if Obama wins Florida and Ohio, this thing is over. There's no way Mitt Romney can win. The media at the time was saying this is a 50-50 thing. Everyone's trying to throw, it's going to go either direction. It's pretty clear that this is a little bit lean towards Obama. This doesn't take into statistics, of course, or polls for each of those states, but it still does a nice job. They even trimmed the redundant nodes of the tree, so they didn't show, once Obama takes Florida and Ohio, they didn't go and show everything broken down. So they really made this consumable for you to read. And I saw something that I thought was particularly interesting because I'm a UI developer, and I'll show you this little video. So this is my mouse moving around, and you can see as I'm moving around, it's highlighting these nodes, but I'm not actually mousing over the little check marks. I'm just in the general region, and it's finding the closest node, and it's representing this. This is curious. So I like this for mainly one particular reason is I discovered that this was interactive by accident. I just happened to mouse over it, and then I learned this is interactive, and I spent another 2 or 3 minutes clicking around, getting a feel for what this data was. If you had to mouse over those little check marks, you probably wouldn't discover it by accident, and you might come to this page and never even know that this was an interactive data viz. This could be a picture for all you knew. So 2012, election night, very boring. I wanted to know, how did they do it? How did the New York Times pull this off? Or rather, how would I do it if I had been asked to do this as a UI developer and my designer came up to me and said, this is what we want? So I started thinking, we want to increase the hit state, basically, of these check marks. So UI developers, we all have a trick up our sleeves. We can add some inner padding to the elements, and instantly their hit state's a little bit bigger. We don't want to have a flat addition of the padding across all of this. The nodes at the top left are a lot bigger and standalone, so that should have more padding than the nodes at the very bottom, which are very, very tiny. So the first algorithm that I came up with was variable size padding. And this is what that algorithm looks like. This is an attempt at it. So for each node in the list, set the node padding to the node radius times 5. No, that's node radius times 5. This is sort of arbitrary. I picked times 5. I wanted, if it was a 10 pixel radius, then it would have a 50 pixels of padding. And if it was one of those small ones that had 1 pixel radius, it would just have 5 pixels of padding. You could definitely mess with that number, and you can even change it to not be linear and make it exponential or any other function. This is what this ends up looking like if I were to draw this out. It works. It did the trick. It did add some padding. It didn't add as much padding as the New York Times did. You can see the bottom left, or there's complete areas of the page which would be very hard to represent with this padding algorithm. But we've introduced a possible bug as well, and that is if the neighbors are very close to each other, the padding could just sit over one and make one just completely not interactive, so you'll never be able to see it. And that's actually a regression that would be filed as a bug, and I'd have to go back and try to fix it and spend months trying to fix that times 5 algorithm in time for the 2016 elections. So this is probably not how they did it. My second guess was, we'll call this one the calculate closest distance from mouse to node position. So this algorithm looks like this. So we'll go through this. This is a, on mouse move we have an event. I grab the x and the y of the mouse position. I go through each node in the list, and then I calculate the distance between the current xy and that node's xy. And then if the distance is smaller than the previous smallest that I've seen, save it off. It's very similar to the largest algorithm. This algorithm actually achieves exactly what you saw on the New York Times website. This is a one-to-one pixel-for-pixel representation of what you saw. But if you're a UI developer, there should be a really big red flag raised that is one hell of an event handler to have on mouse move. Mouse move is firing a lot. And this is going through each of the 512 nodes. You can imagine if there are 10 or 11 states in contention, how that number grows. I'm sure we all know the way that line looks. This doesn't scale. This is potentially bad. So one easy option here is to debounce the handler and only run it once every 100 milliseconds. And you could do that, but now you'd be introducing a lag into this data viz, and New York Times had it flowing just perfectly. So I will call this algorithm technically correct, but there's a performance issue that we can't get around. So what if, and this is kind of a big what if, but what if we could pre-compute every possible XY coordinate in the data visualization and the closest node to each of those. So that is every single Cartesian point, like 0, 0, and 50, 100, and know what is the closest beforehand, before we even start mousing over it. So if the data viz is 1,000 pixels wide by 500 pixels high, that's 500,000 possible positions. We're in a browser here that we have to go through. We got one thread in this browser to compute all this stuff for and save it off. Not to mention memory concerns. This is crazy if you wanted to do that. Like, I would not recommend doing that. But what if there exists an algorithm that takes a very similar input to what the New York Times has, which is these variably placed elements, and produces the exact same output as the algorithm that I had just showed you. If there wasn't such an algorithm, I would not be here tonight talking. So to introduce that algorithm, I have to introduce you to a mathematical concept. I'm sure a bunch of you will be familiar with this. This is called a Voronoi diagram. Does anyone know what a Voronoi diagram is? Good. So a Voronoi diagram is a mosaic. It's the dividing of space into a number of regions. I have a very computer science-y definition for this. A partitioning of a plane around n original points into convex polygons, each containing one original point, so that each coordinate within a polygon is closest to its enclosed original point than any other point. What I mean by so that each coordinate within that polygon is, so each possible mouse coordinate within that polygon, if you wanted to sort of jump ahead here. Another definition would be it partitions a plane around n original points, guaranteeing no overlapping, and while maximizing possible area around each point. This is exactly what I was trying to do with that variable size padding algorithm. I wanted to maximize the area around each point, but guarantee no overlapping, and it would have been nearly impossible to do that. So this is a very simple Voronoi diagram. Typically, there's the 0, 1, and 2 point diagrams, and then 3 and up. So this is a 3-point diagram. And to generate one of these, like those small little algorithms I showed you, this one's a little bit bigger than those other ones. It's a little bit more complicated, although I'm sure there are like 20 of you in the room right now that are on line 6 and moving rapidly down reading this thing. This is called Fortune's algorithm. Fortune's algorithm, it generates Voronoi diagrams by discovering Voronoi vertices. And a Voronoi vertex, it requires a group of 3 original points to be plotted along the edge of a single circle. So we'll show you very visually what all this means. We have 3 original points and a Voronoi vertex right there in the middle. And we could see this circle that I was able to draw. We were able to put at least 3 original points on the edge of that circle. And then in the center of that circle is where we add a Voronoi vertex. One more constraint is that circle needs to be empty. It cannot have an original point inside of it, otherwise it's invalid. So we'll show you how this algorithm works in super slow motion. The algorithm works with 2 main lines. It's a sweep line and a beach line. A sweep line is used in a bunch of different algorithms that you might be familiar with. So you'll see a line that works its way from the top of the page down to the bottom. And its job is to sort of spot out any original points. The data visualization, it cannot view what's below the sweep line. We can, so we can see things, but it can't. So this is the way it works. So there's the sweep line moving down, and there's a beach line that's added to keep track of the points. And we'll see right when I get past these 2 original points, it'll be able to find a circle. And there's the circle it adds. It does not yet know that this circle is empty because it cannot see the rest of the circle. We can. But once it finds out the circle is empty, it will add a Voronoi vertex, and then it connects the dots. So we can see this is a bit more complicated. The sweep line's coming down. And we can see right now that the circle is not empty, so the circle is going to be discarded once it's discovered that it's empty, which was right there. And it just sort of rapidly moves its way down. And this is a this is a very pretty version of it, just because I think this is kind of a pretty thing. There's a lot of stuff going on here. Yeah, somebody implemented this in Canvas and then like made it all step by step in slow motion for us to see, which was just so cool. I've got links in the bottom of the slides for anyone who wants to go draw your own Voronoi diagram and then watch Fortune's algorithm actually work step by step. So how does Fortune's algorithm relate to these 2 gentlemen? In particular, how does it relate to this data visualization? Well, luckily, this is built for the browser. So what I can do is I can actually use my web developer inspector tools that comes with Chrome and inspect these things and actually crack this open for everyone to see. So I'll open up the inspector tools. And what I do is instantly I find this. What's that? Oh, yeah, it gives it away. It's a spoiler alert. So by default, SVG elements, path elements, they have a fill set to black and no stroke, which is like your border, fill and border. And I see when I actually inspected it, I couldn't inspect those little arrows. It actually stopped me. And I was inspecting this invisible to the naked eye, but not to the mouse cursor element. And the fill is set to none, and it didn't override the stroke. Therefore, it's completely invisible. We can't see it. So what I'm going to do is I'm going to add in a stroke width and a stroke. And we can see what the New York Times pulled off here is they drew a Voronoi diagram over this. And these elements that you're seeing here, these are all your standard HTML elements. These are DOM elements. They can be styled with CSS, as I just did in the inspector tool. They can be accessed via getElementById if you had an ID on it. And most importantly is that you can attach event listeners to these things, like mouse enter. And mouse enter, it won't draw the rectangle. It'll actually mouse enter over the polygon that you actually drew. So this particular approach, it's not just limited to data visualization, or it's not just limited to this binary tree. It could be used in many different kinds of data visuals. So this is a scatter plot that the New York Times had. You could imagine how annoying it would be to get your mouse over that Derek Jeter dot up on top. Not the big picture of Derek Jeter, but the dot up there. But New York Times, again, just added this Voronoi diagram. Here's a more complicated line graph. Yeah. At some point, I mean, it kind of gets out of hand, but it definitely has its application. If you had little mouse points over that, it would be impossible to find that particular mouse vertex and get your mouse over it. This just increases the hit size here. This is a 538 released this site, I think, a couple days ago, or maybe last week. And Alison McCann, the developer there, she added the Voronoi diagram so you can interact anywhere on this particular data visualization, and it picks it up for you. So, Fortune's algorithm. Not really a weekend project for someone to implement. You don't have to, luckily. If you use D3, which is the current gold standard in front-end SVG editing, it comes with its own implementation in the geometry package, where you can just pass it an array of positions. And also there's a paper.js, which is a physics library. It comes with a standalone Voronoi library, so you can compute those as well. Historically, though, it's important to note that Voronoi diagrams, they have nothing to do with user interface or hit state. They're actually, they date all the way back to 1644. The first known use was René Descartes. And some of the applications involve, if you were to want to know where to put the next police station in your town, you can figure out what police station would be farthest away from every other police station. They can be used to determine capacities of wireless networks. You can imagine those as different wireless towers and then the networks being its capacity. They even have uses in robot navigation. If those black dots, the original points, are all obstacles, the lines of the polygons are actually furthest from those obstacles than anything else. So if you wanted to make a path to go through things and be sure you won't clip anything on your left or right, they can be used there too. When I was researching these things, I found this story, and I just kind of fell in love with the story. So I have to go into detail on this because it is a very, very cool historical story. One of the first notable uses of a Voronoi diagram happened a long time before Voronoi really put his name on it. But in 1854, this physician named John Snow. So Voronoi was, I think, he put his name on it in the 1900s or so. But John Snow used this in 1854. I found a better picture of John Snow. This is what he looks like. Very handsome. In 1854, there were a lot of cholera outbreaks in London, but in particular, there was 600 people died in this neighborhood of Soho. And Jon Snow was very familiar with this neighborhood. So he plotted all the deaths out on a map. Jon Snow wasn't doing this just for fun. Jon Snow had a theory about germs and disease that was not accepted by anyone, and he was ridiculed for it. So this is his own personal research. This is the map that he actually used. These little black tick marks that you see on the side of some of the streets, those are the deaths per that household or that block of houses or that apartment. So after plotting the deaths out, he plotted the public water pumps. The water pumps are going to be the original points of this Voronoi diagram. So you can see the water pumps in the map right here with the blue arrows. After seeing the data on this map, Jon Snow he further theorized that the cholera outbreak it was coming from a water pump, which was not the accepted theory at the time. The accepted theory in 1854 was disease was spread. It's called the miasma theory. Disease was spread through a noxious cloud that would just go neighborhood to neighborhood, and you inhale the gas and you get sick. So this is what it looks like with some modern aid for the Voronoi diagram. If you drew it and colorized it, you can tell the evidence is it's pretty damning. That one particular polygon has most of the deaths in it. Jon Snow went house to house and even asked people who died outside of that area some questions, and most of them answered that they preferred the Broad Street pump, which is that pump in the middle, or they had friends or the kids went to school in that neighborhood, so they had reasons for being in that, which further cemented this whole idea. And it's important to note, this is not the normal way you would subdivide a city. Doing it based on the water pumps is extremely clever. You would just, in any other way than this particular shape. So it would be very hard to see this, unless, of course, you were Jon Snow. So this theory was crazy. Louis Pasteur, who came up with the germ theory, it's another 10 years before he comes around and really puts this whole germ theory together. And like I said, the popular theory was the miasma theory. Still, though, when they saw the data, when Jon Snow, he convinced them to remove the handle from the water pump, and the deaths stopped in that area once people stopped getting water. They later did some investigations, and they found that a cesspit, this is pre-sewage system, a cesspit was dug too close to the water source, and it was leaking into it. So, even though he stopped to help the outbreak, he continued to be ridiculed. The officials at the time, they said that the idea that disease could be spread through human waste was, and this is a real quote, too depressing. They likely said something to him along the lines of, "You know nothing, Jon Snow." And then we all know the rest of his story. He was banished to Castle Black and swore an oath to the Night's Watch. What actually happened to Jon Snow really was too depressing, though, and I say that kind of laughing. He ends up dying of a stroke 4 years after this in 1858, so he never actually sees his full vindication. He never sees that he was right. In the 1860s, the sewage system was growing, so cholera outbreaks kind of stopped. And when they did happen, they happened in neighborhoods that did not yet have the sewage systems. So this is a newspaper clipping from 1866, which is well after Jon Snow's death. And you can read there, it says, "Not to drink any water which has not yet been previously boiled." This is obviously a departure from the miasma theory, and it's obviously a head nod to Jon Snow. And today, if you go to Broad Street, you can still see the water pump. It stands. It's a historical item. And if you look up, and I think to the north, you will see the Jon Snow Public House, where you can go in and grab a beer. And a beer is a good idea. There was one anomaly in Jon Snow's data, and that was a monastery didn't have a single death, and they got all of their water from this Broad Street water pump. And as it turns out, the monastery, they didn't drink water, they only drank beer, and the fermentation process actually killed the cholera. So it ended up, yeah. So when in doubt, drink beer, and you'll be safe. So yeah, that's it for algorithm number 1, though. We're going to move on to the next one. That's also it for my Game of Thrones trivia jokes, so we'll have to wait for the premiere next week. So moving on. Oh, nope, sorry. Now I'm out of Game of Thrones jokes. That was it, thought I hit that one. All right. So number 2 deals with hierarchical menus. And this is a picture of a hierarchical menu. This should look pretty familiar to most of us. And these should be pretty annoying to most of us, or we should all at least have a solid memory of these really biting us. And I'll show you what I mean by that is that when the menu slides out and you move directly to the call to action, the menu just hides. This is bad. And what you're looking at right here, this is the most popular menu system on the web. This is Twitter Bootstrap, how it comes out. This is used everywhere. And even if I clip the top of the menu item above me, it thinks I'm mousing over that. So if there are two menu systems, now it pulls out the wrong one just on the way there. So the menu hides the mouse. This is annoying. So there's a quote on this by a guy named Bruce Tagnazini. He says, "The engineer who originally designed hierarchicals apparently had his forearm mounted on a track so that he could move it in a perfectly horizontal direction without any vertical component." Yeah. Tagnazini, the guy who said that, he is one of the fathers of HCI, which is like the UX, user interface, human-computer interaction. He wasn't always the nicest person on the planet. He isn't always the nicest person on the planet, but it's hard to argue with him there. So we can fix this. I fixed this before. I think most people have fixed this before. You do a little setTimeout trick. So here's the trick. When you mouse enter on one of these menu items, you clear all existing timeouts. And then you go ahead and you save the selected menu item, and you set a timeout, and you wait about 150 milliseconds for the user to get their mouse to the position, and then you select that, or you trigger the next item, which is to hide that menu. This is the pretty common solution. This isn't anything that's crazy. And you can see in implementation of this right here. So you can see I was able to go diagonally there, and it kept the menu open. So problem solved. But a new problem was introduced, and that is when I'm moving up and down, that menu is kind of lingering around for that 150 milliseconds, even though I have no intention of going there. And you can imagine if there were 3 or 4 of these little slide-out windows and them all staying open on top of each other. We've fixed one problem of moving towards the call to action, but now we've introduced another problem, and that is we've brought in this lag. So here is Amazon's implementation of it. So you can see as I go up and down, it's going instantaneously. And as I'm going towards the call to action, it's being forgiving, and it's letting me clip the items above me as long as I'm moving towards it. So it fixes both of these problems. I get towards the call to action, and I get this instantaneous menu switching. So what we need is we need an algorithm, like Amazon's, that does not interfere with the blue path of moving up and down, but only helps out with the red path when I'm moving towards the call to action. Luckily, a couple of years ago, there was a blog post by a guy named Ben Kamens called "Breaking Down Amazon's Mega Dropdown." And what he did is he went into detail on how Amazon pulled this off, and then how he copied it, pulled it off for the Khan Academy where he works. And this is a basic interpretation of his algorithm. So we have the slope function that we all remember from grade school, rise over run. We have this event handler function where we go and we calculate the upper right and the lower right bounds of the menu. And then we want to calculate a couple of numbers. We need the decreasing slope, which is the slope from the current mouse position to the bottom right, and the increasing slope, which is the slope from the mouse position to the upper right. We also need the previous slope from when the last time that we checked this. So this is something we kind of have to check every few milliseconds to see where that mouse cursor is going. And then this if statement is really where is the meat of this algorithm, is if the decreasing slope is getting more and more negative, which is it's less than the previous decreasing slope, and the increasing slope is getting more and more positive, or it's greater than the previous increasing slope, then we go ahead, we set a timeout for about 10 milliseconds, and we do nothing else. We're kind of inert. If that if condition is not met, then we change menus instantaneously. So here's a visual aid of what this means. Here is our upper right bound box in 1010, and the lower right at 10, -10. Here's our mouse cursor. Here's the slope that we want to go ahead and calculate. So here's a sample calculation of it. So nothing special. The mouse moves, and 10 milliseconds later, we have a new line, and we want to calculate the slope again. And now we want to compare it in that if statement, which is if the increasing slope, which is now 4, is greater than 0.625, we're true. And if -6 is less negative than -1.87, which is true, then go ahead and save that. Don't change menus yet. Keep it open. They might be working their way towards the mouse. You can tell if these two conditions are true, we can safely deduce that the mouse is moving towards the right, which is where the call to action lives. And you could easily change this to be towards the left or up or down or anything like that, but for this example, it's just towards the right. So here's the algorithm again. As long as we're keeping track of the slopes, we can sort of figure out that the mouse is moving towards the right and save them. If that condition's not met, the mouse is either moving down or up or to the left or too far down and not enough to the right. Ben Kamens, he kind of conceptualized it with this little triangle he put on there. As long as the mouse is moving continuously in this blue spot and not stopping or changing direction, it'll keep the menu open for you. So another quote from Tagnazzini is, when I specified the Mac hierarchical menu algorithm, I called for a buffer zone shaped like a triangle so that users can make an increasingly greater error as they neared the hierarchical without fear of jumping to an unwanted menu. As long as the user's pointer was moving a few pixels over for every one down, on average, the menu stayed open. This is very similar to what you saw on Amazon's. The only difference is Amazon also lets you go up instead of just down. The menu's only dropped on the Mac, but sometimes they go on both sides. So this is this buffer zone shaped like a triangle. So this is all in an open source library called jQuery Menu Aim. And you could actually plug this in directly to your Twitter Bootstrap menu system to improve the usability there, which is nice. The algorithm that I showed you is lifted from this particular library. It only comes out to about 40, 50 lines of actual code. So if you want to go read it, the real algorithm yourself, you can. I removed a bunch of the stuff with special options if you want to put the menu to the left and the right and some redundant stuff. There was a really interesting, and I don't say this often, a really interesting comment section in this particular blog post is breaking down the Amazon's mega dropdown. And it started off with this comment by Jake Smith. He says, this was first implemented by Apple's HID team back in the 80s, specifically Bruce Tagnazzini, I believe. He is everywhere. I mean it, he's everywhere. He even comments on this blog post himself. He says, yes, I did invent it back in 1986, and it is firmly in the public domain. So this part always cracks me up, and not in a good way. 1986, I was born in 1986, which means that this was in the development cycle at some point on the day that I was born. And it's been forgotten by almost everyone. Even Apple didn't have it for 26 years. I mean, they didn't have it until last year, I think, or maybe a year and a half ago. They never brought it back. So it's incredible to think that when we're building these user interfaces in the browser and we're recreating these things that we see on other systems, we forget these like minutia almost. We end up making a big difference, and everyone has ended up been bitten by this moving horizontally type bug. And that hasn't been a problem for 28 years. This is before cell phones. This is before web pages and everything. This is such a long time ago. He goes on to say, the OS X team later failed to copy the algorithm, so I'm happy to see Amazon resurrected it. If you are using at least Mavericks, the algorithm is back in your operating system. But when Apple bought Next, they didn't actually, Next didn't use it. They didn't have this algorithm, and they never brought it back over. So it was missing from Apple and Windows. And I don't know if Linux, if GNOME or KDE had it. I don't think they did, but I'm not quite sure. So where would a comment section be without a troll? Hey, Apple, time to sue. And where would a troll be without someone who took them too seriously? Yeah, sure, Apple invented triangles and delay, LOL. So that's it.